In this video, we'll take a look at transformations of functions. If you need to look at your toolkit functions before we start, go ahead and take a look at those. We're going to see how you take the toolkit functions and transform them, or what happens when you add, subtract, multiply, or divide, or multiply by a negative, what happens to the original function. So the first thing we're going to take a look at in transformations is a vertical shift. If you take y equals f of x plus c, that raises the graph of your function by c units. If you take f of x minus c, that lowers your graph by c units. So how this works for a vertical shift, use the graph of f of x equals the absolute value of x. So you know from your toolkit functions that the absolute value of x looks like a V shape. So the original function, absolute value of x. So if we take absolute value of x plus 3, vertical shift means this function is going to move up 3. All of the points move up 3. So our function will look exactly the same, but each value on the y-axis vertically will move up 3. The graph of the absolute value of x minus 2 means every y value is going to be subtract 2, so the function is going to move down 2. So the entire function moves down 2. Each of the individual points moves down 2. So a vertical shift, if you add, it moves up, subtract, it moves down. The next thing we can do to a function is we can move it to the right and to the left. A horizontal shift, f of x plus c, be careful, this actually moves the graph to the left c units. So we're going opposite. If you take f of x minus c, it shifts the graph to the right c units. So if we use the graph, the toolkit function graph, f of x equals the square root of x, let me draw that in. Graph 3 points. We know that 0, 0 is a point, 1, 1, and 4, 2. Those are 3 points on our toolkit function. There's the square root of x. If we're going to graph the square root of x minus 4, this actually moves your entire graph to the right 4. The shape doesn't change, but each of these points moves 1, 2, 3 to the right 4 spaces. So the graph looks the same, but it's moved to the right. And notice we're subtracting inside with the x, not outside of the function. Next, if we have f square root of x to obtain the square root of x minus 1 minus 2, notice we're combining two of these now. The x minus 1 moves the graph to the right 1, but then this minus 2 moves it down 2, so we're combining both of those. So we're going to move the entire graph to the right 1 and down 2. So you start with your original and move each point to the right 1, down 2. And when we do that, then we're going to recreate the graph to the right 1, down 2. So that's the square root of x minus 1 minus 2. So also check your work in Desmos to make sure that your graphs are correct. Okay? So we can move a graph up, down, right, left without changing the shape. Next thing we can do to a graph is we can reflect around the x-axis. We do that by multiplying by a negative. Notice the y's become negative. Or we can reflect around the y-axis. The x's become negative. So notice y's negative reflects around x. X is negative reflect around y. So if we use our toolkit function, the square root of x, 0, 0, 1. If we graph the first graph, f of x equals the square root of negative x, that means all of our x values are becoming negative. That means we're going to reflect around the y-axis. So that means each point, the first point stays where it's at because it's on the y-axis, but we reflect each point, and there's our reflection. So that's the square root of negative x. If we have the negative on the outside of the function, it reflects around the x-axis. So the second function is going to reflect over x. This point stays where it's at. This reflect, reflect. So it matters where the negative is. This is negative square root of x. All right, next thing we can do to a function is we can take a vertical or a horizontal stretch or shrink. So if we're multiplying a function by a number, then we multiply each y-coordinate. It's called a stretch if the number we're multiplying is greater than 1. It's called a shrink if we're multiplying by a number less between 0 and 1. Horizontally, you can think of it the same thing. If we're multiplying by a number times x, if that number is greater than 1, it's a stretch. If it's less than or between 0 and 1, it's a shrink. So we're going to take a look at what's the difference between these two. So we're going to use the toolkit graph x cubed to show in this example. And I'm going to use just 3 major points, 0, 0, 1, 1, negative 1, negative 1. And basically it looks like this. That's our original function x cubed. So if we're going to take 2 times x cubed, we're multiplying all the y-coordinates by 2. So think of the values that we have. When x is negative 1, y is negative 1. When x is 0, y is 0. When x is 1, y is 1. If we multiply each of those by 2, we're going to get, when x is negative 1, y is going to be negative 2. 0, 0, 1, 2. So we're going to take each of these coordinates and stretch them. So 0, 0 stays where it's at, but if we x value to the right one, we're going to go up 2, down 2. So this is called a vertical stretch. So think of it as stretching the graph and it becomes closer to the x-axis. So this is 2x cubed. Okay, so a horizontal stretch, if you think of g of x, 2x cubed, what we're doing is we're multiplying now all the x-coordinates by 2 instead of the y-coordinates. So now, think about your original points, negative 1, 0, 0, 1, 1. If we multiply the x's by 2, I get negative 2, negative 1, 0, 0, and then 2, 1. So if I get negative 2, negative 1, notice this one's stretched horizontally. That's 2x cubed. So a vertical stretch makes it closer to the y-axis. The horizontal stretch made it basically further away from the y-axis. Again, you can use Desmos to check and make sure when you're doing your homework. Next example, use the graph of x squared to graph 2 times x minus 1 squared plus 3. So we're doing a whole bunch of things to the graph of x squared. The graph of x squared is our basic parabola. 0, 0, 1, 1, negative 1, 1, 2, 4, negative 2, 4. So our basic parabola x squared. Okay, you know from vertex form that the vertex, let me write this down. So the graph is going to change its shape. The new shape is a vertical stretch of 2. The new shape is y equals, instead of x squared, it's 2x squared. So we're going to do a vertical stretch. Then we're going to move it to the right 1 and up 3. You know from vertex form that your vertex is at 1, 3. So moving this graph from 0, 0 to 1, 3 means to the right 1 and up 3. So do your stretches and shrinks first and then move your graph next. So the first thing we're going to do is this vertical stretch of 2x squared. So what this means is multiply your y coordinates by 2. So this point 1, 1 becomes 1, 2. Negative 1, 1 becomes negative 1, 2. So let me dot that in. So our graph is going to be a vertical stretch. Now we're going to move it to the right 1 and up 3. So to the right 1, up 3, and then recreate that graph. And that's what we end up with. Okay, again, use Desmos to just help confirm. All right, next example. Graph the square root function, then use transformations to determine the graph of the given function. So this graph, the negative on the outside means it's going to reflect. And it either reflects over the x-axis or the y-axis. If you forget it's on the outside of the function, take a look at your reflections. It's on the outside, it's going to reflect over the x-axis. So we're going to reflect over the x-axis. Then the x plus 6 means we're going to move to the left 6. So we're taking the original graph of the square root of x, 0, 0, 1, 1, 4, 2. We're going to reflect it over the x-axis. That's the first step, and then move it to the left 6. So when you move the entire graph to the left 6 and then recreate it. So that's our new graph. All right, last example. What if you have a graph and you're trying to figure out the transformation? So the original graph is the graph of y equals the square root of x, and it's moved. The original graph would be here, 4, 2. It looks like the shape is the same because we still have a point here and a point here. So it looks like it's been moved to the right 1, up 2. So to the right 1, up 2. So our new function is going to equal the square root of x to the right 1 would be minus 1, and then outside the function plus 2. All right, last idea in this section is something called even and odd functions. A function is called even if for every input x, f of x equals f of negative x. It's symmetric about the y-axis. So graphs that are symmetric about the y-axis means that the y-axis is a reflection line or a symmetry line. So the graph of x squared is an even function. The graph of absolute value of x is an even function. The y-axis is a reflection line. A function is called an odd function if for every input x, f of x equals negative f of negative x. An odd function is symmetric about the origin. So what that means is the graph of x cubed is an odd function. For every point here, xy, there's a negative x, negative y on the function. It's a rotation of 180 degrees around the origin. Another function is the cube root of x. That's symmetric. It's in a 180 degree rotation. For every point xy or x f of x, there's a coordinate x, negative y. Okay? In terms of coordinates with the even functions, for every coordinate xy, there's a coordinate that's a reflection, negative x, with the same y value. So if you want to determine whether a function is even, odd, or neither, you can graph it and take a look. So is the function f of x equals x cubed plus 2x even, odd, or neither? So if we graph it, you can see that if you were to take this and rotate it 180 degrees around the origin, that it would be the same, or for every xy, there's a negative x, negative y. So this function is odd. If you don't have the graph and you just have the function, substitute negative x, and see what your output is. Here I would have negative x cubed plus 2 times negative x. That would be negative x cubed minus 2x. Notice that's exactly opposite of my original function, so that tells me that f of negative x is equal to negative f of x. For every negative x, there's a negative y. Okay? If the function were even, such as y equals x squared, if you substitute a negative x in there, you'll end up with the function that you started with. So f of negative x equals the original function.